All right, thank you. Then we will start with the last Design++ seminar series of this autumn semester. I welcome you all very warmly. Today we have the honor of Dr. Christoph Waibel, who is our in-house speaker. And I will quickly give an introduction. So we have already had these 3 nice talks, and this is the last one of the series. You can also find more information on our YouTube channel, or if you've missed one of the previous talks, you can find them all online. And this is the team that has been organizing these seminar series. It's me, Danielle, Daniela, and Michael. I think it will change for next year, but we will try to continue this seminar series as it has been this semester. So yes, I would like to introduce Dr. Christoph Waibel today. He, as you know him probably, is a senior researcher and teacher at ETH Zurich in the Future Cities Laboratories Global, powering the cities. And he studied architecture in Stuttgart and environmental design and engineering in London, and conducted his PhD in the chair of physics here at ETH. And he's also a lead developer in the Rhino Grasshopper plugin Hive. And this talk today, he will present his current work with this Global Cities Laboratories, where the research is standing. And their goal is to find novel solutions to large-scale urban decarbonization by increasing solar energy production on buildings, or one of their goals. And his talks will focus on how they develop new methods to reach this goal in the interconnected domains of mobility, energy design, economics, and life cycle analysis. And with that, I would like to give the stage to you, and thank you very much for coming here.
Thank you. Yeah, thanks for the introduction. All right, so welcome to the last talk of the Design++ seminar this year. It's about powering the city, a rather big research project with a lot of colleagues who are also sitting here in this room. So if there are detailed questions, they're also the experts to answer them. And first, an introduction of what actually building integrated photovoltaic is. And I suspect that this audience will know what it is, but in the last talk, there was quite a couple of people who did not capture the difference. So let's just have some examples of building integrated photovoltaic. Photovoltaics, you probably know, it's a technology to convert solar irradiation into electricity. And what's the difference to building integrated photovoltaics? Well, it's a little bit undefined, let's say, but it should be on buildings, somehow as part of the building fabric, or attached or integrated into the building fabric. And here you see one nice example where the roof shingles are designed in a certain way to still reminiscence in the old shingle design. Then you can simply put them onto your balcony and still reveal the full aesthetics of solar cells. But you can actually also conceal them entirely. So this one is a tower in Basel by Burkhardt and Partner. And many people would probably not know that this one is a BIPV facade, because you can't really tell. Yes, there are some other examples. This one is by Bolzhauser, an architectural professor also here at ETH, and they use Brise Soleil with PV, also really nicely integrated. And then you have more prominent examples. This Novartis pavilion, also in Basel, where you have a BIPV facade integrated with a media facade. So in the evening, it shines with sparkly LEDs. Also, this one is BIPV. And what's the point of showing you all these examples? Well, I want to highlight the difference to regular photovoltaic, roof-mounted or ground-mounted PV systems. And this one you could quite safely call a mature technology. So there's no real, well, there are, of course, questions around it, but it's a rather straightforward technology to use and to implement. And in contrast to that, if you think about BIPV, well, there's no standard solution. This one is a picture we saw in Singapore. You could also call it BIPV, but there's the standard BIPV facade. Every facade is more or less customized and special depending on the project. And that means if you plan BIPVs, or BIPV facades and buildings, it's more complex. It requires more specialized expertise and more challenges that need to be tackled. And that's why it needs a 360-degree view onto the topic of BIPV. And specifically, we are talking about urban integrated photovoltaics. So anytime it's about buildings, it's of course also the urban context plays a role. And we have a plethora of topics that, there's zero contrast, okay, I can put this aside. Of course, you want to design these facades, and that requires some engineering behind it, some simulation. That's a big topic in our module. You want to look into the technology and solve constructive problems. System integration is a topic, and of course, how it reacts with the urban microclimate is also a topic. And on top of all that, it's also, of course, important which kind of business models you apply, how you ensure social acceptance, and how it all plays into the bigger system of how humans want to adapt this technology. So in this talk, we will have three bigger themes: simulation, optimization, and machine learning. And I will go through each of these three themes now. Behind Powering the City is a really nice, huge international team with Arno Schlüter here as the PI of the project who initiated it. And the PI from the Singapore hub is Francis Busung Lee. And yes, we have a couple of postdoctoral researchers, PhD researchers, and professors who are involved in this topic. And the themes that are covered are, as Vera introduced, mobility, architectural design, engineering, socioeconomics, exactly. So let's jump into the first topic, simulation. And the subtitle is SML-XL for the architects here. It also shows the range of simulation aspects that we cover in this project. And I will actually start with XL. And of course, the first thing that you would want to do is to assess the entire PV potential of a city, let's say. And we did that for Singapore. There's not so much magic behind that. These are quite established simulation programs, Climate Studio in that case. And we simulated the whole city of Singapore in a rather high resolution to figure out what the solar potential is. Now, if you compare that image with that one, of course, you see some spatial differences, which would also result in certain detailed differences in how you perceive or how you estimate irradiation. And that's why for certain typical typologies, we conducted photogrammetries to have a high resolution in the modeling. What we found is, so first of all, you can, of course, plot the whole city and look at where there's more irradiation, where you have a higher potential on buildings. And then you can also split it up into these districts, and maybe let me explain this graph a little bit so it makes sense to everyone. This one shows, so each column is one district, and it actually shows the ratio between energy production on roofs over facades. So anything that is above the dashed line means that this district has more PV potential on facades than on roofs. And that's quite special, especially for Singapore particularly as a dense city. But it means that you can produce more electricity on facades than on roofs, and that's very interesting. And what we can see, of course, there are a couple of districts where this happens, and this is where BIPV becomes especially interesting for us. So if we add all these numbers together, in Singapore, you could actually achieve 20 to 30% self-coverage of the total electricity demand. This is rather on the optimistic side, and we will actually see now in a bit why this might be potentially overestimating the potential. But in theory, it's possible. Which brings me to the next theme, PV under partial shading. This is one of the large challenges in BIPV planning. I guess you see what's wrong on this picture. This one is a BIPV facade, by the way, the black parts. And you see a tree in front of it, and it casts shade, and that means there's no electricity production. And in fact, most of the larger studies, most of the energy system studies in the literature, most of the assessments and simulations, they basically only simulate the irradiation on surfaces, and then they say, okay, whatever irradiation I have my conversion factor, and that's the electricity I can produce. And what that assumes is that each of the solar cells actually produces electricity and is more or less decoupled from the entire module. Well, that's a bit too simplified, because in reality, we have electrical architectures. And for roof-mounted or ground-mounted systems, Usually you only need one inverter. To spare you the technical details, they're all connected in one, and because they have a very homogeneous shading situation, or no shading ideally. Then on buildings, of course, you have very heterogeneous conditions, which means that the current status quo is that you have string inverters. So you string together several modules that are similar in size and irradiation condition, and they then produce electricity or don't produce electricity once one of these panels is shaded. And then you have microinverters where really each module has its own inverter, and even if this panel is shaded, it doesn't matter for the rest, for the remaining ones, because each of them has their own control system. And yeah, a more detailed sketch actually can also introduce bypass diodes, but let's skip over the technical parts. The point here is, if we look at that and simulate these differences, and we've done that, Justin did that here for this roof mounted system, which is not ideally spaced, but it was on purpose, so we have shading. And it means that if we now assume these different modeling approaches, and as I said, most of the studies they use just this very optimistic cell-based approach, you have a difference up to 20% of irradiation. So that's quite a bit. 20% more or less electricity, yeah, that's relevant. So to summarize, there is a significant overestimation of power output if you model it in a too simplistic way, and especially for BIPV, this detail becomes really, really relevant if you want to do it right. Continuing on the small scale, on PV systems, of course, they produce electricity, but they also consume materials. And one of our postdocs, she is specialized in life cycle assessment, and she has decomposed the whole system and looked into the different components, how much each of these components consume, or what their embodied impact is. And we have developed this parametric calculator such that you can actually assess the impact of these different components in a PV system. Turns out the most important part is the PV cell. So over 70% of the entire carbon emissions embodied carbon emissions of the panel is actually the solar cell. And the rest then becomes quite negligible. 15% maybe the mounting system, quite high, but the cell is really the take or break. And that's why, of course, we also looked into the production process of these PV cells, how they are grown. And to make it short, these are highly electrical processes with a lot of electric energy required. And you know where most of the PV cells are produced, currently in China, with a lot of coal electricity. And that's why, if you think about PV modules and you have some opponents saying, oh, they also produce waste and so on, well, there is a large potential to optimize the embodied emissions, actually, if you produce them in grids with low carbon emissions. And let's make a scenario if we produced them in Switzerland. You might be aware that Switzerland is like a transit country for electricity from the neighboring countries, Austria, France, Italy, and Germany, a very important country in this story, because, as we can slightly see with these colors, the final energy supply, only 15% of the electricity that Switzerland consumes comes from Germany. But if you look at that graph, 70% of the entire emissions in Switzerland is from these 15% of electricity from Germany. So why am I telling this? It is important if we wanted to decarbonize the embodied emissions of PV panels, we need to understand how we produce them and under which grid conditions we produce them. And basically, the grid needs to be clean such that we can also produce clean PV panels. And if you know all these things, then of course you will also realize that putting PV is not meaningful everywhere in the whole facade. And this is earlier master's thesis also here at ETH, where we, the student calculated the carbon payback time for each panel. And blue means good and red means really not good. And if you look at the north facade, all the yellow and red panels, they have a carbon payback time of above 30 up to 60 years. And if you consider the lifetime of a PV panel, which is currently you have a warranty for 20 years, then this is never going to pay back carbon-wise. So this is also, again, very important information. And we can think this further, and we can, again, Justin, our talented PhD student over there, sitting there, he likes trees and he wants to save them. And unfortunately, if you plan BIPV, some developers might want to cut trees down because you want to make space for the PVs. And we looked into that. It doesn't make sense. To summarize this graph, this shows the yield, well, basically how much carbon emissions each kilowatt hour produces. And the difference between if you cut all the trees down or if you leave them in the total yield that you can have is quite negligible. But the impact of the trees that you would then lose is so high that you should just not do it. So in conclusion, don't cut trees for PV, at least not now. Also, this is quite interesting, actually. If you look at the three colors, these are the three major technologies, monocrystalline, polycrystalline, and thin film solar cells. And those who have been working a bit with PV, they know that thin film technology is a very inefficient technology. It doesn't produce a lot. But if you look at the carbon balance, it's actually much better per kilowatt hour produced. And also that is quite important information. So this concludes the simulation part. Let's go to the second topic of optimization from buildings to neighborhoods. And for this chapter, we have two examples. Optimization of buildings. I see some MIP students here. You have used Cactus, the framework, the BIPV framework. The story here is, or the idea here is that if you have BIPV facades and you have some certain customized layout, you need to cut these cells into all these individual shapes. Also, if you have a shading situation, then you might want to actually know which PV panels to string together, which not, such that you don't lose on the electricity production. This led to the development of our new video that we have, of this optimal panelizer, let's call it. It's part of this Cactus framework that is still unpublished, but soon to come. And what you can see here is that first you start with the facade and a panelization of the facade. Then you conduct an irradiation simulation. You know how much sun hits the facade. And after that, you start with inserting the cells, the solar cells. This one actually now does a matching of the cells, or of the modules that would go together. And now you see those cells that are stringed together, actually. And well, this has been manual work before, and now we have an automatic tool that does it. And why is it relevant? Because, of course, it makes the whole planning process and production process much more efficient. And actually, you can also then start to optimize these different panels and ultimately cut down on the cost. Now, we actually use optimization a lot on a larger scale, on a neighborhood and district scale. And this is relevant because of the following situation. The most common way that you can use PV is actually you rent out your roof, or you just buy your own panel, and then you consume the electricity on site, and then the surplus electricity you feed into the grid. And that's all you do. But especially in Switzerland, actually, there are a lot of living labs that already do that. There's the concept of solar neighborhoods, or ZEVs, Zusammenschluss zum Eigenverbrauch. And what that means is actually that buildings in a community, they come together, they connect each other electrically and also actually with other energy carriers, and start to share energy and trade electricity and other energy internally. Other elements that are really important also here are, of course, these other distributed energy resources, such as battery systems, and some kind of control systems, community aggregator. But let me show you, okay, then we conducted this on a couple of case studies in Singapore. These 9 different case studies, some more commercially focused, some industrial, some more residential, and some more mixed. And also that I think I will summarize a little bit. It's basically an optimization framework, which some of you here are also familiar with. And you require inputs such as building demand data, irradiation data. And what we wanted to study is how important these different strategies in a solar community are. So how important is it if you can share energy, if you can share the load within the district? How important is it that you actually introduce some kind of trading mechanism and trading pricing mechanism? How important is it that you actually start coupling the electrical side with the thermal side, and so on. So that was the basic research question in this part. And yeah, what you can see here is an example of a Singaporean neighborhood, very dense. And the blue buildings are those that have surplus electricity in that case, and they're exported to other buildings that pop up in yellow. So what it means is these buildings, they just have too much electricity, and they sell their electricity within their own neighborhood to these neighboring buildings for a better price than if they would export it to the national grid. And therefore, there's a financial incentive to do it. You just get more money if you just sell it to the grid. But also from a grid perspective, this has certain benefits because you can, you don't cause strain on the national grid. By the way, this is an exhibition that is still running until April, I believe, in the Hill top floor. If you want to play around with an iPad and have a look, feel free. Okay, so what are the results for these 9 neighborhoods that we looked at? The total reduction of levelized cost of electricity, so that's the cost per unit electricity, is quite significant. Sorry, this is just a table, but let's look at the big numbers. 40% in one case. So we can really make electricity, PV electricity, much more expensive, much cheaper if you introduce these strategies into a neighborhood, into a solar neighborhood. What we also found is that actually storage systems, batteries, are one of the major key technologies that drive down the cost. So really you want to make sure that you introduce flexibility into your system, for example, with storage systems. So there's one, the bottom neighborhood, the cost reduction caused by batteries is 50%, so that's the major driver here. Also, if you look at these numbers, to summarize it, solar self-sufficiency as well increases significantly once you introduce these trading mechanisms, these sharing mechanisms, and if you don't only rely on the grid. Right, that summarizes it basically. Solar neighborhoods is a good idea. That brings me to the last topic, machine learning. Also here we have a subtitle, more data. Of course, this one is about data. And also here I will talk about 2 projects in our team. One where we use a lot of mobile phone data, and the other one is about facade design. And let's start with the mobile phone topic. Well, to begin with, actually this has something to do with electric vehicles and PV. And the question is, what do PVs have to do with electric vehicles? Well, we want to charge our electric vehicles with green electricity, with PV and not with coal electricity. And turns out there might be some interesting synergies. If the sun shines and you don't need to drive around with your car, you can charge these cars and discharge them in the evening when there's no sun. And we have actually done that also in an optimization model. And again, to summarize it, it's really important that you implement the right policies and control mechanisms, because if you only react to the electricity price, to the wholesale electricity price, you actually charge at those times when there's no sun and when you're actually only increasing strains on the grid. But there's a huge potential to do so, to couple PV, also local PV production with EV charging, and that's generally a really good idea. What we rely on for these model links is actually mobility or predictions on mobility patterns. So we need to know when do people drive around where, and that's actually where we use mobile phone data from all your cell phones. So not in Switzerland, but in Singapore, this data is slightly more accessible. And what you can see here is each of the colored dots is actually one literal person walking around. Well, it has been anonymized. And I think this one is also synthetic data, so there's no problem when sharing it. But this data exists, so we can people can really track, or the telecom companies, they can really track people around, and you can see where they are, basically. Anyway, this is good for us because we can build mobility patterns out of it. And we can use routing algorithms to use these data points, and they're usually quite noisy, and you have to filter them a lot. But if you apply certain algorithms, what you can do is then predict the mobility paths of people for different days in the week and for different seasons. And if we do that, we can actually end up with the mobility demand for the whole Singapore, electric vehicle mobility demand in that case. And that's, again, very useful information if you wanted to couple that with local PV production. The chance that we see here is, of course, that that's the central business district, CBD, where it's very yellow. So you have a lot of demand for mobility. The idea and the motivation here is, of course, that we want to couple local PV production with local charging demand, and again, to reduce strains on the grid. So much about mobile phone data. Now coming to the last topic of also one of our esteemed PhD colleagues here, Aicha. And what if we only had a picture of a facade? And we want to click one button and then have a BIPV facade. Well, that's what she's working on, but we're not there yet. There are some steps in between. And one is actually we want to understand the image. And we're talking here about segmentation and grouping them into different categories. We want to know what's a window, what's a sill, what's a door, and so on. And only then we can work on the other magic. Many of you probably will have tried out Midjourney and DALL-E and all these things. We also tried that for BIPV design, and it's not very successful yet. As you can see in the bottom row, these are supposed to be the BIPV variants of the top images, which are the normal facades without PV. And yeah, I can't see too much BIPV here, so it's not really working. The existing models are not sufficient yet, but that's the motivation for us. We want to get there. And as I said, the first step, what I'm going to present now is this part of the segmentation of these images, and we want to understand where are these, or what are the parts of this image which are interesting for BIPV. Well, we used machine learning models, in this case, pix-to-pix model, to understand or to segment the image into those parts which are facade and BIPV relevant. And if we do that and we do some more correction and we do a color content analysis, we understand, okay, blue is always facade where we can put PV on. And what we're interested in is if we're using the segmentation technique, how does it compare to more common tools that are actually being used a lot also in Switzerland, such as Sonnenfassade or Sonnendach, or just these standard values saying that 40% of the facade in a multifamily house is accessible. And we wanted to question and challenge these numbers and say, okay, if we use segmentation, can we get better, more accurate numbers? This is a result for 100 buildings, and blue is always the available facade. These dashed lines are the different benchmarks from common practice, SF Sonnenfassade. So they report like 30% or 40% available area for single-family house and so on. And what you can see is that there's, of course, a lot of variability. So these simplifications wouldn't really make sense in a detailed or in a particular case. That's a conclusion. The facade availability varies significantly. If we now apply that to calculating PV potential or electricity production, and we did that now here for 10 buildings as an example, let's zoom in into this one to explain this graph. What you can see here with these 3 bars is the non-solid one is using this standard assumption of 50% of the facade would be available for PV or BIPV. So that's like the standard assumption. And the solid bars, the dark yellow and the light yellow, those are the values that we calculate using the segmentation technique. And as you can see across all the bars, the stripe bars is always significantly different to the ones if you use these segmentation techniques. And that also reflects in the calculated PV potential. If you use these wrong numbers, obviously you end up with quite high overestimations of PV production. So, as a conclusion for this part, more accurate estimations are possible with using these segmentation techniques, and that's actually quite important if you wanted to make reliable predictions. Well, the next step is still in production, and let's wait for some more things in the future. Just to mention the solar potentials part, also this is where it connects to other work in our team, for example, the cactus framework that you've seen. and another machine learning-based solar model that I'm not going to introduce now because it actually is shown in other talks. Yeah. So, as a conclusion, BIPV research in our Powering the City module, we have found that BIPV in particular is quite unique. It's not the same as designing a normal PV system. It introduces a set of very unique questions, a set of unique problems that we're trying to tackle in this module. And it's also important that you look at them all at the same time because of how they relate with each other. Also, as I hope you might have seen that simulation optimization and machine learning are complementary and necessary tools in all this process. And you can't do everything with machine learning, you can't do everything with simulation, but it really needs this plethora of different approaches to answer all these different sub-questions. And with that, thank you for your attention. And this is actually the whole team of Powering the City, also with many students who have contributed to this work. Thank you.
Thank you very much for the nice presentation. Now I would open up the floor for your questions, if you have any. If you don't, I have also one question. Oh, sorry. I think I will go ahead and then I will let you ask. Have you thought about adding PV to infrastructure, I don't know, retaining walls or bridges in the cities or something like that? Because I feel like there's a lot of available surface there, usually that's not in use.
Yes, we intentionally actually excluded that from our research because it would, again, well, we're more interested in the urban and building context. But you're right that, oh yeah, no, of course, yeah. Actually, we have one, Max in his master thesis, he actually looked into infrastructure in Zurich, infrastructure, like bridges and railways. So, but it's more a fringe topic for us, and we are really focusing on the building context, actually.
Okay.
Yeah.
Okay, good to know.
Thanks for the talk. It's also nice to see an overview after a while since I haven't seen some of this past work. Of course, I'm naturally interested in the neighborhood. Yes. So I'm really curious to know how you selected the communities in Singapore for your study. And was that related to the BIPV production potential? And does that also consider roof PV? Yeah, exactly.
Yeah. So yes, roof PV is also considered. The selection was based on having a different set of neighborhoods, so we can understand how the results also differ depending on the neighborhood composition. There's no solid, we didn't do any like clustering or deep data analysis to show the maximum variability of these neighborhoods, but it was more, Pi mal Daumen estimation, saying this one is a commercial district, this one is a residential district, this one is an industrial district. But we wanted to have a large range of different districts, so we understand also how these concepts work under different conditions.
Did you also have the energy consumption data from these districts, or was that also estimated?
No, that's CA, City Energy Analyst. Yeah.
Okay.
From Martin.
Nice. Okay. I also had another question related to the transport model.
Yeah.
That you used. You said you were using cell phone data. And I'm kind of curious how you couple that, because I know in Singapore most people actually commute by public transport or maybe taxi, but that's a little bit out of their control. And is there a large electric vehicle fleet in Singapore nowadays? It's been a while since I've been there, so.
So no, not yet. There's not a huge EV fleet, and you're right, cars are anyway very expensive in Singapore, so not many people have them. Yeah, most people do commute with, of course. But still, actually, we have run it with different EV penetration scenarios, and even with like an entire EV coverage, if all the cars were EV, then, well, the point is we have to work with scenarios, but of course right now there's There are not a lot of EVs, but the government really pushes for an electrification of the private transport sector. And as for your first question, which was about how we predict EV patterns?
Well, so it was more the question of, is this actual information? And
Yes.
I guess more or less how you're using the cell phone data to correlate with vehicle data.
Yes, exactly.
Or vehicle, like how to use that as a proxy for vehicle
Right.
movement.
So for each ID, for each person, you have a timestamp, you have a location, so you can really say where each, and you usually have certain moments when you get a ping. It's when people use certain apps, for example. And then you can log all these points on a map. For example, in the top right image, all these dots are specific logs. And if we know the time it takes from one point to the other point, then that's how we can make assumptions whether this person used a car or a taxi or was walking. And in this case, for example, in this neighborhood, everyone's walking, obviously. They can't drive a car around there. But because we know the timestamps and the distance, we can make assumptions on when someone would have used a car or a taxi.
Okay.
And then you actually have these open source routing engines. If you have then these points, then you create your path, optimized path. And if that matches with the logs, then that's how we know it makes sense.
Okay.
Yeah.
Cool.
Thank you. Are there further questions? You probably are all the experts here. You don't have questions on your own research. Well then, yeah. I have just one final slide. We do not have the next presenter yet for next semester, but do stay tuned. The series will continue, and I want to wish you a nice upper row in the back. There is some prepared, and Merry Christmas and a Happy New Year.